Greetings, everyone. This is the first session in the afternoon, and it's great to see everyone here. Please join me in welcoming Jon Brewton, founder and CEO of Data², to the stage. Uh, as a pioneering individual in the next generation artificial reasoning technology, Jon is revolutionizing the way organizations harness the power of their data. With a unique blend of military, academic, and industry experience, John brings a distinct perspective to the world of AI and data analytics. From his time as a US military veteran to his roles as an engineer, strategic advisor, and executive in the oil and gas industry, John has developed a deep understanding of the complexities of high reliability sectors. As a leader of Data², John is driving innovation in transparent, explainable AI solutions for defense, energy, and critical infrastructure. His global expertise spans multiple continents with a proven track record of implementing cutting edge technologies in various industries. Today, John will share his insights on Data²'s advanced analytics with graphs from pilot to production. Get ready to learn how semantic graph databases can unlock the full potential of your data, reduce hallucinations, and drive trust in AI driven decision making. Let's give a warm welcome to Jon Brewton.
Thank you. I appreciate the introduction. So I'll jump in. Just want to make sure that you guys can hear me okay and you can see the slides on the screen. I can, but I just want to
Yes,
validate.
yes, it's
Perfect.
all good.
Perfect. All right. So this is me, as you heard. Probably an overly generous introduction, but if you'd like to connect with me, you can on LinkedIn. Here are my details. You'll have this after the presentation as well. So, agenda today, we're going to talk about AI reliability challenges, a little bit around the root cause nature of how these things manifest and how they really persist within the way things are designed today, how graphs can be an unlock, ultimately how TMMi principles and maturity model can be applied to how we develop and actually release some of our solutions that we create. Technical implementation, architecture, a little bit of the roadmap on how we build solutions as a company, a little bit on the case study side for the energy sector, just to kind of give you an application and practice, and then measuring success. How do we do that, and what are we paying attention to? So I'll jump right in, but really appreciate the opportunity to chat with you guys today and hopefully show you something a little bit different than you've seen before. All right, so let's talk about the fundamental challenge. Hallucinations in AI are a problem. The fact-based nature of the returns are a problem. And I and we as a company consider these a fundamental challenge to preventing broad AI adoption in critical industries, especially high reliability industry. Um, on the hallucinations front, I'll start with sort of a sobering statistic. OpenAI's recent simple QA benchmark confirmed that even the most advanced, most recent models still hallucinate at alarming rates. Anywhere between 53 and 81% of the time, you're having responses that aren't factually grounded and have interjected content beyond the scope of what you've asked for. This isn't just disappointing for high reliability industries like defense, energy, and sort of the government and intelligence capacity where we operate on a day-to-day basis is disqualifying. Just as a tone setter, ask yourself which part of your business can withstand being incorrect the majority of the time. It's rhetorical in nature, but the problem we're trying to solve as a company. On industry impacts, this really explains why 73% of organizations are citing accuracy and reliability as their top concern for AI adoption, and rightfully so. In mission critical environments, the consequences of misinformation aren't just inconvenient, they can be dangerous, catastrophic in many instances, and deadly, depending on the application. So, for context, in the energy industry, decisions based on incorrect data can impact millions in infrastructure investments and your overall profitability. In defense, inaccurate intelligence can really compromise mission success and put lives at risk. So this is a broad fundamental problem. And the problem isn't just prompting techniques or reasoning methods that many of the sort of research papers that you'll see are focusing on. It's architectural in nature. Traditional LLMs operate on a statistical prediction rather than verifiable knowledge structures. They're designed to minimize uncertainty or entropy in their outcomes, not to manufacture or maintain factual accuracy. So the real question here is, what accuracy rate would you need to confidently deploy AI in your most critical operations as a company? Is 60% enough? Is 70% enough? Where are you going to get this accuracy? Depending on the application, your answer might be closer to 99%. And that's really where we come in. But I think it's more fundamental. We have to understand the root cause. So why do LLMs hallucinate? And why do we sort of have this persistent problem? To solve the AI reliability challenge, we really need to understand why LLMs hallucinate. The root causes go far deeper than sort of most organizations will realize, and addressing them requires more than surface level fixes. First, LLMs are trained on internet scale data with wildly varying accuracy. If anybody's used Grok recently, you'll get returns that are anchored on somebody's response from a tweet. They learn patterns, not facts, which means they're statistically modeling what words should follow the words they produce based on the context that they understand, and not reasoning about truth. This is a fundamental limitation in their design. To put it bluntly, these models weren't built to be accurate. They were built to be fluent and to provide answers. These models also suffer from a thing called context fragmentation. Think of it short-term memory loss during complex reasoning. As reasoning chains grow longer, the models lose track of the earlier steps, leading to contradictions or errors. It's a troubling example that we've observed personally, and even when LLMs can correctly retrieve from a contextual understanding the information that's required early in its reasoning process, as you continue down that sort of chain or path of reasoning, it'll often start to contradict itself just a few steps later. Third, LLMs have no clear delineation between what they know and what they don't know. Unlike us, who can say, I don't know the answer to that question, or I don't understand what you're saying, these models are designed to generate answers. So this is why you'll see chatbots confidently citing non-existent research papers or inventing facts. They have no internal mechanism to distinguish between established facts and statistical inferences. The last thing is they're mostly missing context. These systems lack specialized knowledge frameworks for vertical industries. They lack specialized terminology, regulatory requirements, an understanding of the operational context of any given vertical market. And this is particularly problematic when you're dealing with AI solutions that are deployed in mission critical spaces where the nuance associated to that context matters. If we dig a little bit deeper, to use an analogy, traditional methods for trying to sort of buttress this or really sort of create some sort of sustainable contextual awareness are sort of non-persistent in nature. They tend to be something that you have to rework over and over and over again. Traditional RAG approaches use vector embeddings and chunking. And so just contextually, as a good analogy, whenever you're interfacing with a large language model, it's roughly akin to dumping a puzzle out in front of the language model, hiding the box cover, and then asking it to make sense of all of these disparate pieces of information. Because of that, it's kind of no wonder that they start to hit accuracy ceilings of around 80%, and that's with additional sort of context-laden approaches to creating some contextual awareness. But I want to challenge these assumptions. Hallucinations are not inevitable. They're a product of an architectural approach that prioritizes statistical prediction over verifiable knowledge structures. And that's really where we start to unlock something. Understanding these root causes are fundamental to understanding how you can address and create persistent solutions around them. And that's where semantic graph databases come in, which is what we'll explore next. So, what are semantic graph databases? Now that we understand in principle the root causes of hallucinations, let's explore why graph databases provide an architectural foundation needed to solve these challenges. So let's focus on knowledge representation. At its essence, graphs store information fundamentally different than, say, traditional relational database systems. Rather than rows and columns of isolated data, information is represented as interconnected entities and nodes and edges that are connected to one another tangibly. And those relationships mirror how humans actually think about the world. And this is a crucial piece of the puzzle because it allows us to move beyond statistical prediction models, the traditional AI applications, to structured knowledge foundations that can be verified, traced, and expanded over time. The other big thing that graphs allow you to do is preserve context. The power of a graph database lies in their ability to maintain multidimensional relationships between data points. Unlike traditional systems where relationships are implicit or require complex joins and a lot of manual data engineering work to keep these things present and functioning, graphs make these connections explicit and you can navigate them. Think about your organization's knowledge and how it actually works. Nothing exists in isolation. Every piece of information is connected through complex, multifaceted, multifunctional relationships. And graphs capture that reality in a way that a traditional database cannot. The other thing that they allow us to do is verify reasoning chains. Now, we have a proprietary process as a company that's patented and sort of, I think, the leading approach to how you would want to do this. But at a super high level, we can address hallucinations because we understand how the information environment is connected. And we have a very prescriptive process for how we engage large language models from that fact-based representation. So when an AI makes a claim, we can follow the exact path through the knowledge graph that led to that conclusion. This is a bit of a game-changing application. Instead of hoping that an AI response is accurate, we can validate the exact reasoning change that was executed and validate the data sources used to produce the answer. This allows us at a graph level to incorporate industry-specific ontologies, taxonomies, knowledge at scale and schemas. And this means we can build specialized knowledge structures for energy and problem-specific applications within the energy domain, and defense and problem-specific applications within the defense or intelligence space. So this allows us to capture sort of the unique nuances within the structure of that vertical market, the terminology, the regulations, the operational context of these domains. And that directly addresses one of the root causes we identified earlier, which is the missing or ephemeral nature of domain-specific context in general-purpose LLMs. So without a graph, you're left chasing sort of an ever-moving target that requires significant and perpetual data engineering. Every new data source requires specialized knowledge engineering to manually map and define those relationships. That's not only expensive, it creates an activity bottleneck around what you can do with your data and when you can do it. It does create some decision drag. So at Data², we're really focused on unifying semantic structures, enabling relationship discovery, supporting schema evolution, ontology evolution in an automated capacity, and scaling horizontally within a universal data model to prepare these environments for operating from a ground truth and being able to fact base and understand where these answers are being generated from. Oh, sorry about that. All right. So we'll move forward to how are we applying sort of the principles of the stage maturity approach to AI systems. The path to reliable AI isn't achievable in a single leap. It requires structured and really evolutionary approaches to deployment. And that's why we developed a maturity model for AI reliability that is inspired by the test maturity model integration framework that's provided on the screen here. The overall model provides a clear progression path from unpredictable outputs to reliable mission critical insights in deployment at scale. TMMi's helped organizations systematically improve their testing processes. These frameworks offer a structured roadmap towards increasing the reliability of your AI systems in deployment. So whereas level one represents where many organizations start their AI journey using out-of-the-box AI models with minimal controls and verification, you can really get down to level four pretty quickly and understanding, just how you can measure the quantitative impacts and trace the AI reasoning at scale. And so I think it all starts with having a plan at the end of the day. And I have no idea why it's jumping around, but it allows us to follow a maturity model that we can check ourselves against. And I think a lot of your success is dictated by how well you plan for success. So we'll jump ahead and I'll talk about sort of the technical implications of what we do. And we can look under the hood at sort of the high level architecture that enables the level of AI reliability that we've discussed. This diagram shows how we integrate the graph database with large language models to create a system that fundamentally addresses hallucination problems and the fact-based nature of recall within the structure of our environments. The overall architecture, what you're seeing right here is the review platform. It differs fundamentally from traditional AI implementations. Rather than simply connecting an LLM to a retrieval system, we've created a bidirectional ecosystem where a graph acts as both a knowledge source and a verification mechanism. So starting on the left, you can see how sort of private data flows through our specialized encoders for different types of information. We have an unstructured coder, a structured coder, a time series coder. This multimodal approach ensures that we can capture all the data types that exist in an enterprise environment, not just text or not just structured information. Because we can combine these things into a unified knowledge representation layer in the middle section, this is really where the magic happens. We can identify the entities within the structure, whether they're people, assets, concepts, events, it doesn't matter. We can tie the evidence within the structure of this unified data environment together, whether that's structured, unstructured, temporal, time series information, doesn't matter. And we understand the relationships, the connections between the entities and the evidence and what that means for just how we can actually contextually recall the right pieces of information. So this isn't just storage, it's a living, evolving representation of your organizational knowledge. And it's integrated into a single, unified, universal data model. On the top, you'll see the LLM integration process. Unlike traditional approaches where LLMs drive the process, in our architecture, the semantic graph guides the LLM through it. So we go through entity extraction and natural language and relationship mapping. We understand from a context perspective and the question you asked, what pieces of that puzzle are relative to the query that you're trying to pass to a large language model. Our reasoner formulates a precise graph transversal path, and it starts to subsegment from the broader data model the pieces of the puzzle that we need to answer the question that you've asked, and we pass that in a very controlled way to the large language model. And whenever we do that, we understand what we pass the system, what's being used by the system, and then it allows us on the right side to understand what the system returned so that we can score it. So all the claims are traced back to specific evidence in the graph. All the answers are checked to be a fact-based answer and within the structural knowledge that we used in asking and interacting with that large language model, the questions that we're asking. The system differentiates between factual statements and general inferences, and potential hallucinations are flagged before they're returned to the user so that we can get them out of the system. I will say, just in general, whenever we go through this process, we have a hallucination scoring mechanism that allows us to say there are hallucinations, are there, or there are not. But for the last 6 months, we haven't seen any hallucinated content returned in the productionized applications that we built or any of the test things that we've been doing. So this architecture is unique. It allows us to retrieve information, reason over the knowledge graph. Traditional RAG systems simply operate a little bit differently, whether it's just off of simple vector embeddings or chunking from a text perspective. Those are inherently disconnected. They're methods that are trying to create some connective tissue, but this system allows us to achieve roughly zero hallucination rates and really is a step change from even just general graph rag applications in this structure. So it really is something that's quite different. The implementation roadmap, I'm not going to spend a ton of time on just because I think everybody probably has some questions. So I'll try to jump forward. But having a structured process for how you build and deploy anything that you're going to build and deploy is exceptionally important. And this really follows sort of the TMMi staged improvement philosophy. So let's talk about case studies. As we talked about this a little bit earlier, here's a concrete example of this approach in practical application. We had a client, a major oil and gas operator, facing a challenge that's pretty common across the energy sector. They purchased a set of companies to incorporate into their broader company. Across those companies and those acquisitions, they acquired more than 3,000 new assets. And really, at a top line, they had an understanding of what these assets brought from a revenue perspective, but not necessarily any of the micro details of any of the individual assets themselves. So they were drowning in data, multiple systems, production logs, maintenance records, financial data, regulatory compliance data, performance data, all of these things set in segmented silos that were inherently disconnected from one another and were in different forms and formats from their legacy systems that they had in place. So we took that as an opportunity to implement review. So we built a domain-specific energy sector graph for this customer. And it wasn't just about connecting their data. It was about structuring it within the context of the industry and the industry-specific knowledge required to solve the problems that they wanted to get to. And the graph really enabled us to integrate structured data from their enterprise systems with unstructured data from their reports and their documents and operations data from their SCADA systems and some of their deployed assets. This allowed us to get a full cycle understanding of the value chain. And at the end of the day, we were able to save this company in the first year of operations about anywhere between 27 and $30 million. We achieved a 99.9% reduction in AI hallucinations when working through our platform. And the context relevancy in terms of the recall from a natural language perspective went to roughly 99%. And insights generation was roughly 98% faster. Some of the problems people were working in a disconnected capacity took on average 20 days, and now they take roughly 2 minutes. And so this approach changes the efficiency horizons of what you can do with AI and really starts to underline the importance of what a graph can buy you as a fundamental data model that you can use to integrate into your existing data systems. So really great success there. We don't do anything without measuring how well we do it. So we've adopted this framework trying to quantify AI reliability and the improvements that we're able to generate. And this really allows us the opportunity to focus on accuracy. We measure hallucination rates, the fact verification scores. We understand how the system generates information, when it generates something incorrect. We have human in the loop validation, so we can cycle back to the overall data model to see if anything has been mislabeled, mistagged, or miscategorized. And this allows us to sort of maintain in a persistent manner a unified data model that allows us to reason at sort of superhuman scale. So I'll try to just close real quick. Hallucinations are present, they're persistent, and they're really fundamentally an architectural problem with how you engage large language models. What we found is we can eliminate them almost holistically if we engage in the right way. Now, we have a patented process for doing it, but graphs are a critical unlock. Now, creating knowledge graphs is a non-trivial exercise. One of the things that we did from a patented perspective is we have a patent pending program that allows us to auto-generate a knowledge graph for your specific data environment, roughly 80 to 85% efficacy automatically. So we can start to reprocess your legacy data and get there quite quickly. The other thing that we really try to do is focus on business results. And so I think we have a staged approach and a staged process for how we actually like to build, deploy, test, modify, and keep things ever present. But falling back on the fundamentals that are preached by TMMi and some of the things that they can give you is a great place to start. So I'd say I'd stop there and let you guys ask any questions. But at Data², we're committed to providing not just a product, but a pathway to innovation that redefines what's possible in these environments. I believe this approach represents the future of AI reliability. I don't see a tangible, scalable path forward without some sort of graphical interface that you can build that has persistent connective tissue within the structure of your organizational data model that's multimodal in nature and that crosses functional boundaries. So I'll stop there. Thank you for your time. I appreciate the opportunity to talk to everybody and look forward to answering any questions. Feel free to connect with me offline or connect with the company. We're always happy to talk to people about what we do.
Hey, John, we do have a few questions, and thank you for the
Okay,
insightful
cool.
talk. So let's go with the first question. How do you think the hallucinations already existing in the Gen AI solutions will impact the building of agentic AI frameworks?
I think they're going to impact it pretty substantially. If I'm being completely honest, I think agentic system scale is all about the ability to know that systems are persistent in nature, they're organized in a certain way, the interaction that you can generate as a byproduct of the workflow that you're trying to execute or the agentic like workflow that you're trying to create is static in nature. And a lot of agentic systems have potential scale issues whenever you look at deployment because they're really looking after what I would say is a little bit of a foundational issue with data. Like data is a little bit messy. Your ability to scale any of these systems is really dependent on connected, contextualized, and high fidelity understanding of your information systems. The models are only good as they're only as good as their infrastructure. So scale brings complexity. Each deployment environment introduces unique dependencies. So even if you're operating, say, like on an agent that's developed by Schlumberger, for example, for oil and gas customers, there may be differentiation in the application of that system from company to company. And so you'd have to modify these and even business unit to business unit. And I think there are real potential issues fundamentally in how these things are going to scale in application. It's just there's a lot of underlying structural issues that are going to have to be addressed for us to reach this age of super intelligence where everything sort of works seamlessly.
Thank you. Uh, we are almost at time, but we'll take one more question and then we'll wrap it
Sure.
up. How can we begin to implement graph databases within our organizations if we do not have the in-house expertise? Should we upskill or outsource the talent?
Graphs are non-trivial. So it really isn't something that you could do if you don't have any awareness or fluency on. And even if you tried to build it, the specialization of knowing how to build these things is pretty tightly held by a few companies. We are partnered with Neo4j, but the beauty of what we do is we use Neo4j's database structure and we have our own graph creation process. So we automate the graph creation process and then we curate that graph on subject matter expertise boundaries and conditions for the problem that we're trying to solve. So we can automate it. So if you're worried about creating graphs for your organization, you can reach out to us. Neo4j is probably the best graph database system in production, mainly because they work on labeled property graphs, which can create a lot of semantic fidelity within structure. And that's why we use it. But if you want to build a fast graph, you can reach out to us. You'll have my contact details. I think we might be the only people in the world that can do that quickly. Full stop.
That's really nice. We'll end
Yeah.
with that. Thank you so much, John,
Yeah.
for sharing your expertise, uh,
Yeah.
your insights on leveraging semantic graph databases to drive trust in AI-driven decision making has been extremely enlightening. We appreciate your time and participation for Test Formation 2025 and request all the audience to continue this conversation and any questions you may have through social media and reach out to John and Data Square if you have any needs that um, they can solve. Please join me in thanking John with a virtual round of applause. Thank you, John. Have a good day.
Thank you. All right, guys. Thank you.